Tree and graphs are nonlinear data structures. In order to visit through all the vertices of the tree, you have traversal techniques. The first one is in order, pre-order and post-order. Similarly, in order to visit through all the vertices and edges of the graph, BFS and DFS algorithms is used. BFS is nothing but breadth first search algorithm. DFS, depth first search algorithm. So, why do you require to use this breadth first search algorithm? In order to visit through all the vertices and edges of the graph in particular fashion. So, this is similar to level by level tree traversal. In order to implement this BFS, data structure queue is used. So when you do the BFS traversal, it redraws trees in tree-like fashion, which results in two kinds of edges. One kind of edge is called tree edge, other one is cross edge. Cross edge connects previously visited vertex other than its immediate predecessor. So we'll see with the example here. This is the example given to you. Now we'll see how this BFS algorithm is implemented in order to traverse these vertices of this graph. So first start with 1. This is being visited. Then visit through all the adjacent vertices of 1. 2, 3, 4 is being visited. Then 2 comes first. So, explore all its adjacent vertices, that is 5, 6. Then for 3, 7, 8. Then for 4, it is 9, 10. So, look at the order in which you are visiting through all the vertices of the graph. First with 1, 2, 3, 4. Then 5, 6. Then 7, 8. Then 9, 10. This is how you are visiting through the vertices of the graph. That is level by level. We'll see the pseudocode of BFS algorithm. Initially, mark all the vertices of the graph with value 0. This indicates vertices of the graph is being unvisited. Use the global variable called count in order to say that these vertices is being visited. Mark that vertex with some count value. So initially count is equal to 0 because none of the vertices of the graph is being visited. So for each vertex V in vertex set V, if V is marked with value 0, then invoke BFS algorithm. Increment count value, then mark V with count and initialize Q with V. So initially you are invoking the algorithm with V, and now that you are pushing V into the Q. So you are required to perform these steps while Q is not empty. So for each vertex W in V adjacent to the front vertex, if W is marked with 0, increment count by 1, mark W with count, add that W to the Q. How long? For every adjacent vertex to the front vertex, you are required to do that. Then remove the front vertex from the Q. So how long you are required to do like this? Till Q becomes empty. I'll explain this algorithm for the previous graph. So initialize all these vertices with value 0. Then what you are required to do is call this BFS algorithm with this vertex 1 and Next step is increment the count by 1 and push this one to the queue data structure. So now 1 is marked with value 1. This is included into the queue. Now while queue not empty, now queue is containing one element, that is 1. So for each vertex W in V adjacent to the front vertex, so which is a front vertex now, currently it is 1 itself. So for 1 itself, so which are all the adjacent vertices of 1? 2, 3, 4. So insert that into the queue and mark these two vertices with value 2, 3, 4 respectively. And then since all the elements of 1, that is all the adjacent elements of 1 is already explored, now remove this from the queue. Now in front 2 is there. For 2 again, adjacent vertices are 5, 6. Now remove this from the queue. Now in the front 3 is there. Adjacent vertices of 3 is 7, 8. Push it into the queue. Now, so since all the elements or all the adjacent vertices of 3 is explored, remove 3 from the queue. Again, now what will be there in the front now? 4. So for 4, the adjacent vertices are 9, 10. This is being pushed into the queue. So now with that, remove this. Then finally 5 will be there in the front. So no more adjacent vertices for 5. Remove 5 from the queue. Then remove 6 from the queue. Remove 7, 8, 9, 10. So that is what is being explained here. While the queue is not empty, you are required to explore all the adjacent vertices. Okay, so how? By level wise. So I'll illustrate one more. We'll see here. So this is the graph. For this we'll illustrate. For this graph, I'll explain how this BFS algorithm will work. So start with A. Push this A into the queue. Then explore all its adjacent vertices C, D, E in lexicographic order. So C, D, E. Push that into the queue. So with that, you have explored all the vertices, adjacent vertices of A. So remove A from the queue. So when you remove A from the queue, in front C will be there. For that, adjacent vertices are A, D, E, but already A, D, E is marked with some, A, D, F. A, D is marked with some number. So only one vertex which is adjacent to F, which is marked with 0, is F. So push that into the queue. So now the order in which you are pushing into the queue is 5. Now you have explored all the adjacent vertices of C, so delete this from the queue. Now in the front D is there. For D also you have explored all the adjacent vertices. Then in front E. So for E, the adjacent vertices are F, A, F, B. A is explored already, F is explored already. The next one is B. So include that into the queue. So next E is deleted and F, then B. So with that, the queue becomes empty. But there are some more vertices which is not marked with any value. So first is start with G. So insert G into the queue. For G, the adjacent vertices are H and J. So insert H and J into queue. Then delete G. Now when you delete G, on front H will be there. For H. Already J is explored. The only one which is left out is I. So include or push that into the queue. So this is how the traversal looks like. So we started with A, then C, D, E is being visited, then A is removed. So for C, the adjacent vertex is only one is now F, and then for E it is B, then G, adjacent vertices are H, J, then for H it is I. So we'll see for one more graph here. So for this graph, BFS traversal is applied here. Start with A. Adjacent vertices of A is B, E. For B it is C, F. And for C it is D, E. D, J. And for D it is H. Okay. So now here, for this tree traversal, you are getting two trees. This indicates that, look at both trees are disjoint trees. So set of disjoint trees is called forest. When you apply BFS traversal for a graph, if you get a forest, then this indicates graph is disconnected graph. That is, it is not connected. So when you apply this BFS traversal, if you get cross edge like this, then the graph contains cycle. And one more property you can derive from BFS algorithm is minimum edge path. So you can find minimum edge path by applying BFS algorithm. So here, look at here, to reach to G, starting from A, start invoking this BFS algorithm for A, for A. So with that, you are getting this as the resultant tree. So look at here, from A to G, how many edges are there? 1, 2, 3. So 3 edges are there. Okay. So minimum path edge is 1, 2, 3. So in BFS algorithm, it is similar to DFS. When it is implemented using adjacency matrix, then complexity is theta of p square, and when it is implemented using adjacency list, complexity is theta of modulus of e plus modulus of e. This yields single ordering of vertices, that is, order in which you are adding the vertices into the queue in the same order you are deleting from the queue. So applications of BFS is same as that of the DFS, that is two common properties. One is you can check whether the graph is cyclic or not. The second property you can derive from BFS traversal is you can check whether graph is connected or not. And distinct property of BFS is, so you can find minimum path edge. Thank you.